welcome to another episode of Double Award Physics. In this one we're going to talk about the echo principle. Dead simple this one. Two things you need to know: that speed equals distance divided by time, where this little slashy thing means divided by, and you need to know that waves bounce off stuff. You know those two things, you're in business for the echo principle. Alright, so let's imagine a situation where we have, let's do the boat one. Okay, so we have some water, because water is black and completely flat, and we're going to put a boat on top of the water. So bear with me whilst I draw a boat. Clearly that's not a boat. Ta-da, one boat. Okay, and let's make it a convincing boat by filling it in an appropriate color, like green. So therefore we have a boat. If you're still not convinced by the fact that it's a boat, let's give it a sail. Voila, one boat. Top of the line. Shrink my boat down a bit, otherwise I'll not have room for the rest of my diagram. Okay, so let's assume that this is a high-tech fishing boat that is running on sail power, and we're going to put a shoal of fish beneath it. Okay, so let's say this is what a fish looks like. Clearly that is extremely fish-like. We can do better than that. We can do better than this as a fish. Can you see what it is yet? Okay, one fish. No, we did say a shoal, so let's get a few fish down there. Awesome sauce. Okay, now what I want to do is I want to locate those fish. Alright, so as I travel over them, what I do is I'm going to send out little pulses of sound. Okay, I'm not attempting to communicate with the fish, I'm attempting to locate them. So I send a little longitudinal wave, if we remember our classification of waves. A longitudinal wave, which is sound, and it travels down to the fish. Okay, now by the laws of reflection, when one of these waves hits a fish, the wave will bounce off. Okay, the wave will bounce off and it will return upwards, or at least some of it will return upwards to the boat. Okay, so let's put that in, and let's do that as kind of ready waves. Okay, so we can see the difference between them. And let's get properties of that, line style. There we go. Okay, so if we try and track this wave all the way back up, okay, then it will travels down, bounces off, travels all the way back up. Okay, now if we work on the principle that we know the speed of sound in water, okay, I mean we are on the boat with some exceptionally complicated equipment. We are timing the how long the pulse takes, so we have some form of timer. Okay, then we know the time, we know the speed, and we can find the distance that the wave has traveled. Now the super important thing to remember is that when you calculate the distance traveled, what you calculate is the distance that it travels all the way down and all the way back up again. Okay, so to find the distance to the fish, you're going to have to divide this line by 2, so that you just get the distance all the way down. Okay, so let's do an example. Let's say that we have that we send out a pulse, so a pulse is sent. Speed of sound in water, let's say it's of the order of 1,500 meters per second, or thereabouts, and the time taken for the reflection to be detected is 1.2 seconds. Detected. My god, it's so bad, it's actually the third one down. Okay, so what we're going to try and do is we're going to find out how far away are the fish. Okay, so here we go. We use speed equals distance divided by time. Okay, for the mathematically not so confident, that is our triangle over here, that we have speed, distance, and time. Okay, so I'm looking to find the distance. Okay, so I'm going to cover up distance. So let's just do that. Okay, and that leaves me with speed times time. Okay, so distance equals speed multiplied by time. So the distance is going to be the speed, which is 1500, multiplied by the time, which is 1.2. So the distance equals 1,500 plus a fifth of that is 1,800 meters. I think that's right anyway. Okay, now that's the distance that the wave travels. The actual distance that the fish are away, remember, is half of that. So distance to fish, move this up slightly, is equal to 1800 divided by 2, which equals 900 meters. And that's all there is to it. Okay, now you can get a variety of different ways of being asked this question. It can be using this. This is called sonar, okay, which is using sound and water. Okay, you can also get it using radar, which is if they have aircraft. Okay, so oh god, I have to draw a plane. Okie doke. There's airplane with a wingy bit. It's a technical term. Form of nose cone. You've all just realized that you've actually logged in to watch me play around with kind of art on the computer using random shapes. It's like being first year at school again. Yeah. Little tail fin job there. And yeah, this turned into an awesome plane. I am so good at art. I don't know why I became a teacher. I have no idea. And we need a little domey bit. Domey bit may be a problem. There's one domey bit. I fill this in. Order bring to front. Order bring to front. If this works, it will be a minor miracle. I'm so bad at art, it's not funny. Right, there we go. Awesome. Right, so if you have an airplane, I don't know why I drew an airplane. If you have an airplane, then you can sometimes get a little radar mast here, and it sends out a radio wave. Okay, radar standing for radio detection and ranging, so it will send a wave out. That wave shouldn't be expanding, but it is. And the wavelength's all over the show, but it hits the plane and then bounces back. Okay, exactly the same system, and they can use the fact that they know the speed of light, which is the radio wave speed, and they know how long it takes for it to get a signal back, so you can detect where the plane is. Awesomes. Okay, the course also requires you to understand some stuff about how this is used in industry. Okay, so this is one way it's used in industry. If this was an ultrasound material, okay, so this is an ultrasound source, an ultrasound detector, set slightly far apart from each other, then what you can do is you can send a sound wave in. Now you know that a sound wave travels at a certain speed in a solid, so that's fine. When it hits a crack, because that's got edges to it, then you will get some bounce back from that. Okay, some will refract through it, as we'll find out in later videos, but you will get a reflection as well. Okay, and by measuring the time between when you send the pulse out and when you get your reflection back, you can get an idea as to where this little crack is, or whether there's a crack there at all. Okay, so the idea is that you put this on, and ideally nothing comes up in your detector, meaning there's no crack anywhere. But if you get a reflection back, then you can locate where the crack is. Okay, so that's an ultrasound use for industry, which is finding cracks in materials. In medicine, probably the most obvious one is to use for fetal scans. Okay, so this is a scan of an infant inside its mother, and look at this little cute hands, this little eyeball that hasn't quite come out right. Okay, this is a kid inside its mother, and by using a series of ultrasounds, you can detect where all the various stuff is. How heavy you get a reflection tells you whether it's skin or bone, so a computer can build you a pretty good image of what the baby looks like. Alright, I think that'll do us for this one, so stay tuned.